Hi everyone, I am Sheeba Varghese, Assistant Professor, Department of Electronics, MES College, Marampally.
Hi everyone. Now we are going to discuss the last topic of the network theory, stability criterion for the net active networks. We all know that the stability of a passive network is determined by the position of the poles. If all the poles lie on the left half of the S plane, then the network is said to be stable. Otherwise, it is unstable. But for an active network, it is not very easy to determine the position of the poles directly. In such conditions, we use the Routh-Hurwitz theorem, which is known as the Routh criterion, for determining the stability. Now, we will see the Routh criteria and how can we determine the stability of this. Consider the polynomial q of s is equal to b0 s raised to 5 plus b1 s raised to 4 plus b2 s raised to 3 plus b3 s raised to 2 plus b4s plus b5. In this case, the polynomial is of the order of 5 since the highest power in the polynomial is 5 and b0, b1, b2, b3, b4 and b5 are the coefficients. The next step is that we have to write the root array. For that, we take the even numbered coefficients of the polynomial as the first row elements. In this case, the even numbered coefficients are b0, b2 and b4. And the second row elements are the odd numbered coefficients. These are b1, b3 and b5. Now look at this array. Here the first row elements are b0, b2 and b4. The second row elements are b1, b3 and b5. Then there are four more rows here and the elements are c1, c2, third row elements, d1, d2, fourth row elements, e1 is the fifth row element and f1 is the sixth row elements. In this case, the order of the polynomial is 5 and the root array contains 6 elements, 6 rows. And in this case, the elements of 3 to 6 rows must be derived from the first and second row elements. And for that, we use a specific algorithm. And using this, we can find C1, C2, D1, D2, E1, and F1. And for that, C1 is equal to B0, B2, B1, B3 divided by B1, which is equal to B1, B2 minus B0, B3 divided by B1. And C2 is equal to B0, B4, B1, B5 divided by B1, which is equal to B1, B4 minus B0, B5 divided by B1. Similarly, we can calculate this D1 and D2 also. Then D1 is equal to B1, B3, C1, C2 divided by C1, which is equal to C1, B3 minus B1, C2 divided by C1. And D2 is equal to B1, B5, C1, 0 divided by C1, which is equal to B5, C1 minus B1 into 0 divided by C1. And E1 is equal to C1, C2, D1, D2 divided by D1, that is equal to C2, D1 minus C1, D2 by D1. And F1 is equal to D1, D5, E1, 0 divided by E1, which is equal to E1, D5 minus D1 into 0 divided by E1. And we can generalize this algorithm. Then to find the element in kth row and jth column, it is required to know the four elements. These elements are in the row k minus 1 and k minus 2 and in column 1 and j plus 1 column of the array. The above process is repeated till m plus 1 rows are found in root array where m is the order of the polynomial. According to the Varghese theorem, the number of changes in the sign of the first column to the right of the vertical line in an array moving from top to bottom is equal to the number of roots of q of s is equal to 0 with positive real part, where q of s is the denominator polynomial of the network function. To get a stable system, the roots must have negative real part. According to Varghese criterion, the system is stable if and only if there are no changes in signs of the first column of the array. This requirement is both the necessary and sufficient condition for stability. Now we will see an example. Consider the denominator polynomial of the network function, which is q of s is equal to s cube plus 2s square plus 8s plus 10. We have to determine the stability of this network by using the root criterion. For that, first we form the root array. Here, the even coefficients are the coefficients of s cube and s. Well, that is the first two elements of the root array, and the odd coefficients are 2 and 10. These are the second row elements. Then the third row and fourth row are C1 and D1. Now we have to find the C1 and D1 from the first row elements 1, 8 and the second row elements 2, 10. For that, we use the algorithm. C1 is equal to 1, 8, 2, 10 divided by 2, which is equal to 2 into 8 minus 1 into 10 divided by 2. That is equal to 3. Then D1 is equal to 2, 10, 3, 0 divided by 3. That is equal to 30 by 3, which is equal to 10. Now, we can complete the root array by giving the values of C1 and D1. Then the root array becomes 1, 8, 2, 10, 3, 10. Then look at the first column elements. These are 1, 2, 3, 10. Here, there is no sign change in the first column. All are positive values. Hence, there are no roots with positive real parts. Therefore, the network is stable in this case. Now we can see another example. In this case, the denominator polynomial is given by q of s is equal to s cube plus s square plus 3s plus 8. In this case also, the power of the system is 3. Therefore, there are 4 rows in the root array. Then first we form the root array. For that, we take the even coefficients of the polynomial as the first row elements. In this case, the even coefficients are 1 and 3, and the odd coefficients are 1 and 8. And these odd coefficients are the second row elements. The third and fourth row elements are C1 and D1 respectively. To find this C1 and D1, we use the algorithm. C1 is equal to 1, 3, 1, 8 divided by 1, which is equal to minus 5. And D1 is equal to 1, 8 minus 5, 0 divided by minus 5, which is equal to 8. Now we can complete the root array. Then it becomes 1, 3, 1, 8 minus 5 plus 8. Here, there are two sign changes in the first column. One is from 1 to minus 5, that is positive to negative. Then the other is from minus 5 to plus 8, it is minus to plus. There are two sign changes in the first column. Therefore, the two roots have positive real parts. When the system has positive real parts, the system is unstable. Therefore, the system is unstable in this case. Thank you.